Hey everyone. So I had a question about answering this example question from lesson 4. I'm just going to write that in here. All right, this is from lesson 4, elastic and inelastic collisions. So the example problem I chose is a little complex just in terms of how many steps it takes to kind of solve this. But the main thing that we're looking at is we're looking at two objects. One, you have a smaller object, this 12 kilogram toy train, right? And it's moving with a velocity of 2.4 meters per second. And then it collides head on with a much larger train that has 3 times its mass. And that was at rest, meaning that it was moving with 0 meters per second. One thing that we know is that this collision is perfectly elastic, meaning that just within this statement, we know that all momentum is conserved and all kinetic energy is conserved. So we're not losing anything, which makes this a slightly easier formula to solve. What we're trying to do is we're trying to calculate the velocities of the two cars after the collisions. Now, I know in the lesson I provided some of the steps. It did kind of skip a lot of the basic algebraic steps, so I'm just here to kind of break it down into really fine detail to kind of show how we get to the final answer. All right, so for this particular problem, we do need two formulas. We have our conservation momentum formula, right, which is just the momentum of the first object plus momentum of the second object, right? That total will equal the momentum of the first object plus the momentum of the second object in total after the collision. Same is true for kinetic energy, right? If we know the kinetic energy of the first object plus the kinetic energy of the second object, then we have a total amount of kinetic energy before collision, and that's going to be equal to the total kinetic energy after the collision. So, knowing our formulas, let's go ahead and plug in numbers we know. Let's start with the momentum formula. So using this formula up here, okay? And we're going to plug in just the numbers that we know already. All right, so we're going to start with our first mass is 12 and our first velocity is 2.4. And this is going to be plus our first mass, which is 36, and our velocity, which is 0, equals, right, we know the mass. We are not going to know the velocity, right? That's part of what we're finding. We do know the mass of the second object, but again, do not know the velocity. All right, so our next step is just solve from what we have here. All right, so 12 times 2.4, we're going to get 28.8 plus 0, because 36 times 0 is 0. And this is going to equal 12 times velocity 1 plus 36 times velocity 2. Okay, a couple things already, right? We can't combine 12v1 and 36v2 just because as far as we know right now, they are two different velocities. What we can do, however, is we can try to isolate for one of these two velocities. Right? I'm just going to go with our first velocity here. So let's say what I'm going to do is I want to get that velocity 1 by itself. So I am going to subtract 36 v2 from both sides. So then I end up with 28.8 minus 36 v2 equals 12 v1. And then I'm going to divide both sides by 12. And then I end up with 2.4 minus 3v2 equals v1. Make that a little neater. Okay, so I have a formula here that I can use in my future. Just makes it a little easier to see. All right. So what I want to do is I ultimately want to plug this formula in to this other equation up here. But first, let's go ahead and plug the numbers that we know into that equation, and then we can kind of solve and simplify. All right, so we start with, I'm just going to write the equation again down here just to make it so we don't have to keep looking back and forth. Okay, equals 1/2 mass velocity squared plus 1/2 mass velocity squared. All right, so let's plug in numbers we know. All right, we know that our first mass is 12. Our first velocity is 2.4 squared plus 1/2 36 times 0 equals 1/2 12 VI2 plus 1/2 36. All right, now I can imagine some of you guys might be asking, why would we be using two separate formulas that look similar, right? In this case, the kinetic energy formula, right? We have half of the mass times velocity squared, in part because both these formulas have the velocity of our object, and we know whether we're talking about momentum or we're talking about kinetic energy, right? The velocity is all going to be the same, right? Whether, it doesn't matter how we're viewing the object, it's still going to be moving at the same speed, right? So that's why we're able to use this other formula here. Again, one quick thing I can do to just very much simplify this is we have 1/2 like kind of going all throughout here. So let's say I can multiply this whole side by 2 to kind of get rid of the 1/2. And remember, whatever we do to one side, we have to do to the other. So that gets rid of that. So then we have 12 times 2.4 squared plus 0. Right, so that's all done for. 12 VI squared plus 36 V2 squared. All right, we can further simplify. 12 times 2.4 squared. 2.4 squared is 5.76 times 12. We're going to get 69.1 equals 12 VI squared plus 36 V2 squared. Now again, in this case, one of our goals is that we want to get rid of all the numbers that we have so that we can just get VI isolated again, so we can use this formula back up here. So what we're going to do is we're going to divide basically everything by 12. And so what we end up with, dividing both sides by 12, we get 5.76 on this left-hand side, and then we get VI squared plus 3 VI squared here. All right, now at this point, we can take this formula that we found way back up here, and we can plug it into our value for velocity 1 right here. So what this ends up looking like, it looks like 5.76 equals, let's go look at it, 2.4 minus 3v2 squared plus 3v squared. Oops, this is 2. All right, now remember, when you are squaring stuff that's in the parentheses, sometimes people can get a little confused. Just remember, this is essentially what you're doing. You have basically two sets of these parentheses now. Okay. So we still got 5.76 on that side. What we gotta do is we have to start multiplying our numbers in. So 2.4 times 2.4, we get 5.76. 2.4 times negative 3v, we're going to get 7.2, and it's going to be negative 7.2 v2. All right, and then we get negative 3 v2, kind of same thing. Okay, multiply negative 3, okay. We get plus 9 v2 squared. All right, and this plus 3v2. I'll be consistent with my colors. Okay, so now we can simplify kind of all the stuff that's in here, right? Because right now it just still looks like a big mess. We got 5.76 still on this side, 5.76, nothing to kind of simplify there. Negative 7.2 v2 minus 7.v2, right? We can combine those. Missing a decimal point. Okay, and then these two both kind of have the same variable, right? Both have v2 squared, so this is going to be, we can add those together. We get 12 v2 squared. All right, so now what we really have is we have kind of a quadratic equation, which we could use quadratic formula to kind of solve this, but again, we don't even have to go that far. What we're going to do here, we can subtract 5.76 from both sides to get rid of that, which leaves us with 0 equals negative 14.4 v2 plus 12 v2 squared. We can add 14.4 v2 to both sides. All right, so we end up with 14.4 v2 equals 12 v2 squared. In this case, we can go ahead and a couple different things you can do here. But let's do it in this particular order. Let's go ahead and divide both sides by 12. Actually, we can just do this. We'll just divide both sides by 12v, right? Because that is a common factor. All right, so then we end up with, okay, 14.4 v2 divided by 12 times v2 equals 1.2 equals v2. All right. Whew. That was a lot of work. So now we have the velocity of our second object after the collision. All right, so we still need to figure out the velocity of our first object after the collision. Again, we can go back to this formula that we found here. I'm just going to be a little lazy here. Copy. Okay, so we can plug this formula into our equation for V2, right? So we can plug this into right here. So we end up with 2.4 minus 3 times 1.2 equals VI. We end up with, let me figure this out, 2.4 minus 3 times 1.2. I get 3.6 to VI. Figure that out. We end up with negative 1.2 equals VI. All right, so our final answer after all that work is that after collision, velocity of our first object is going to be negative 1.2 meters per second. Velocity of our second object is going to be 1.2 meters per second. Now, the reason why one is negative, one is positive, it just means that they're going in opposite directions. So basically, that first object that was moving hit the larger object and then kind of bounced backwards at 1.2 meters per second. Whereas the other object was bounced forwards at 1.2 meters per second. So, that is our final answer. A lot of work. Typically, we'll not see a question that requires that much substitution. But again, a lot of you guys who've been in algebra, algebra 2, or algebra 3, 4, this is nothing really new. All right. If you guys need further help, let me know.